Hello everyone. This video is continuation of my previous video where I have showed you how to write a script for emulating ARM64 binary. In this video I will explain you about unicorn hooking APIs and how we can hook and trace each emulated instruction. Along with this we will see how to resolve unmapped exception which occurred because of external dependencies. And if you are interested in more such videos, then don't forget to subscribe this channel. Now before getting started with our today's topic, I want to explain you one more important point. So we have this crack underscore password binary which we are using for the emulation, and by using the file command, if we see what type of file it is, we see that it's a ELF 64-bit LSB PIE executable. Now please note that it's a PIE executable, which stands for position independent executable, and this basically means that the binary and all its dependencies are loaded into random locations within the virtual memory each time when we execute it. But for our demo purpose here, we don't want this PIE bit to be set. So in order to disable it, we need to recompile our sample C code, which is crack underscore password dot C, and disable this PIE bit. So for that I am using ARM64 Linux GNU GCC cross compiler, and by passing this no hyphen PIE attribute, we will tell this compiler not to enable this PIE bit, and then as usual we will pass our output file. Let's say crack password underscore no PIE, and our C code, which is crack password dot C. So now we should be able to see our new binary, which is crack password underscore no PEI, and if we see the file type of this one, you will see that now it's not PIE executable anymore. But since it's a new binary, we need to analyze it again in the Ghidra just to see whether any offsets has been changed, which are likely to happen. So let's open up the Ghidra again. This is our old executable which we were analyzing. So I am going to import this new file, which is crack underscore password no PIE. Okay, okay, and let's try to analyze it. Yes, analyze. So now if you see, the image base address has been changed. Now it's starting from 4 lakh, and if we go into our main function, we see that offset has been changed. So we need to tell our script again the start and the end address of this main function. So in our script, initially we have this address as a start and this address as end address, but now we will use this as our start address. Okay, and end address would be all the way till return, so it's going to be this one. Okay, now one more thing we need to change, which is this executable name, because now it's crack underscore password underscore no PIE. So we will pass this, and now the length of the program name bytes has been changed. So in our print statement, instead of 10 bytes, let's say I will print 12 bytes, and yeah, hopefully everything should work fine. So let's try to run our script again. Okay, and yep, looks like everything is working fine. So the segments are created here, and the arguments have been set, and we are getting our invalid memory fetch exception. So to resolve this, first we need to understand about unicorn hooking APIs. So let's open up our presentation once again, and I will walk you through some basics of unicorn hooking APIs. So unicorn provides multiple ways to perform hooking, and we have these different hooking IDs which we can use. First one is hook underscore INTR, which stands for hook interrupts. So let's say if we want to hook interrupts or system call events, then we will use this hooking ID. Then we have UC underscore hook underscore INSN. This will be used for hooking a particular instruction. Next we have UC underscore hook underscore code. This will be used if we want to hook a certain range of code. So for example, you want to trace the code starting from, let's say, 10,000 to 20,000, then you can use this hook ID. Then we have UC underscore hook underscore block. This will be used when we want to trace a basic block. For example, let's say you want to trace main function, so we will pass the address of the main function and it will trace the code until the function returns. Then we have hook underscore mam underscore read underscore unmapped, and as the description says, this will be used to trace the code when memory read operation will be performed on unmapped memory. Similarly, we have some other hook IDs related to memory operations. Um, Maybe we can cover all these hooking IDs in detail in some other video if you are interested, but for now let's just focus on hook underscore code because this is the one which we are going to use in our script today. Next, the Unicorn Hook API takes one callback function as argument. Now, this callback function can be of two types. One is for tracing the code and other is for hooking the memory. First type of callback function takes three arguments. First one is the instance of Unicorn engine. Second one is the address where the code is being executed, and the last one is the size of the machine instructions being executed. And if you don't know this size, then you can pass 0. Now for the second type of callback function, it takes 5 arguments where the first 3 arguments are same as above, and the fourth argument is the value. This value will be the data which is being written to memory, and then the user data. This user data will be passed as argument to the tracing APIs, which we will see in the next slide. So if you see here now, we have this hook underscore add API. So in order to tell Unicorn about the hooking, we need to call this API, and we will pass our hook type, which could be any one of the hooking IDs. Then we will pass the callback function, which we have defined above according to these, and then we have our user data, then the begin and end addresses. These begin and end address will basically tell the Unicorn from where to trigger the hook and when to stop the hook. So let's see this in action now. Coming back to our script, let's try to add a hook here before our emulation starts. Always note that you need to set this hook before the emulation starts because otherwise it won't trigger. So you see hook underscore add, and it will take hook ID. So unicorn dot, I am going to use hook underscore code because we are basically emulating the code within this range of addresses, so that's why I have chosen this hook ID. And then the second argument this API takes is the callback function. I am going to name my callback function as hook instruction code. Now the remaining three parameters, user data, begin and end, are optional, and mostly these are required for other hook ID types. For this hook ID, we can only pass these two arguments and this should work. So let's define our callback function here, hook instruction code, and as explained previously, the callback function takes three arguments. First one is the unicorn engine instance, second one is the address, and third is the size, and then user underscore data. This user underscore data we can leave blank if we don't have anything to pass in this object. Now if you remember, at the very beginning of the script we have imported some dependencies, and one of them is Capstone, right? So now we are going to make use of this Python module in our callback function for disassembling the instructions, and I will quickly walk you through its official documentation on how we can use its API for disassembly. So I have the documentation already opened here, which is from capstoneengine.org, and this tutorial is for Python language. If you are using any other scripting language, then other tutorials are also available on this site, so you can check them out. So here in this basic sample, if you see, they have imported the Capstone module, which we have already done. Then here they have initialized a code variable which is having the instructions in byte format, and then using this CS API it has initialized the Capstone engine and passed the architecture x86 in 64-bit mode. So similarly, for our purpose we will be using architecture ARM64 and whatever the mode which we will be using. Then using this instance of Capstone, we are going to call disassemble function, and it will take two arguments. First one is the code in bytes and then the size of the code. So coming back to our script, we are going to do the same thing through the Capstone module. I am going to call this CS API, and it will take CS underscore architecture ARM64, and the mode which we will be using is CS underscore mode ARM. Alright, now I am going to store it into MD variable. So now this MD variable will be having the instance of our Capstone. Now one thing to note here is that by default Capstone do not generate details for the disassembled instruction. So if we want information such as implicit registers, read or written, or which group the instruction belongs to, the mnemonics and the opcodes, all these details will be available only if we will set the md.detail flag to true. By default it's false, so we have set it to true here. This hook instruction underscore code callback will be called every time before executing the instruction, right? So with each execution, this callback will be having the address, size and the user data, and the address will be the address of the instruction which is going to be executed along with the size of the instruction. So now we are going to make use of these two variables in order to read the instruction from the memory. So if you remember, through unicorn mem underscore read API we can read any memory address, and here we are going to read the address along with the size. right? And then I am going to store it into the data variable. And if you remember, this disassemble API of Capstone engine only takes bytes as parameter, so we need to convert this instruction into byte format. For that I am wrapping it into bytes function, and this will give us the instruction into byte format. So now through md.disassemble function we will pass data, and what will be the second argument, the address, right? So here I am going to pass the address. This will give us an iterable data structure which contains information about the disassembled instruction like its opcode, mnemonic and stuff like that. So we will iterate over this structure to get these information, and then we will print it out on the console. So what I am going to do now is simply iterating it through for loop, and I'm going to extract out the mnemonic and the opcode. So for that, let's try to do it in a clean way. So I am going to store it into instruction variable, and let's format our string, tab string, and then I dot mnemonic comma I dot opcode. Okay, so this will give us the mnemonic and the opcode in this format, and now we will print this out. Okay, just to eliminate this from other print statements, tracing instruction at 0x and then the address. So this will be useful if we need to figure out at which offset this the executed instruction is at. Okay, and then the instruction itself. Okay, cool. So everything is done, and the hook should trigger when we start emulating our binary. Let's see it in action. Da, da, da. Okay, so as you can see now, our hook got triggered and it has printed out all the instructions which were executed till this point before the error occurred. Now we know that this is the last instruction which is executed, and it's present at offset 4B0. And if we go into our Ghidra and go to that offset which is at 4B0, this one, it's a branch X17 instruction. One thing to note here is that since it's a very small program, we are able to trace all the instructions here, but in case of a real program, the binary would be usually very big and it's not really feasible to print out all the instructions in the console. So it would be better if you write down all the traced instruction into a file instead of printing it on the console. If you are following and if you have the same output as above, you have noticed that the execution ended up with an error, namely UC underscore error underscore fetch and map, and the last executed instruction is branch X17. Now we do not know where does this X17 lead to. One way to figure out where this X17 lead to is by printing out the value of this X17 register, but it's not going to help us So the best assumption that we can have is that something happened before this instruction which made the code execution stops. So what really happened here? Let's try to backtrace the executed instructions one by one and see. At 4AC, X16 register is being initialized with some arbitrary value. Then at 4A8, X17 register is being initialized based on the X16 register plus some offset. Then at 4A4, again X16 register is being initialized. Then at 4A0, stack is being created and it's initialized with X16 and X30 before calling the function over here. So nothing seems suspicious here, so let's go back a little bit more, and if you look here we have this branch instruction again at 4cc, and if we go into Ghidra and check for this offset which is 4cc here, it's pointing to str length function, right? So we can assume right away that something is wrong with this strlen function, and we are going to hook it and re-implement the code in Python using Unicorn. Whenever you face this kind of error while executing your code with Unicorn, the easiest solution would be to hook the missing function in order to execute a custom function that will be executed instead, right? So in other words, our only solution here is to implement strlength function in Python and execute it whenever strlen function is being called during the emulation. Now if you don't know what the function does, the easiest and quickest way to understand the function definition is by looking its manual page. So let's say we want to look for strlen, so just type the function name and search for Linux manual, and you will see that it has this manual. And if you go here, it will tell you that strlen function is used to calculate the length of a string, and here its syntax, it, size underscore t is the return type and it takes constant character pointer as argument. Then the return value would be the number of bytes in the string, right? So based on this description you can create your own logic for the function. So for that, let's come back to our script and let's try to create some utility functions, and I'm going to define it at the top here. The first one which I'm going to need is read ASCII string, and based on the address we are going to read the string value. So here what I'm going to do is simply I will pass some address and then read the value of the address using mem underscore read API of Unicorn, and I will keep on reading it until I will get null terminating string, because all the strings will be ended with null termination. So what I'm going to do is I'm going to create a result variable here which will be used to store the final result, and then I'm going to run a loop, then using the mem underscore read API I'm going to read the value from this memory address, and the size would be 1 because we are reading it 1 byte at a time. Then I am storing it, let's say, in x variable, then increment our address by 1, right? So now it will point to the next address and then we will read it again. But before doing that, we need to check if the value which we have just read is our null terminating string or not. So we can do that like this, and if it's a null termination string, then we will simply return the result. Otherwise, we will append this byte in the result. Okay, so I hope you understood this logic. It's very simple, just reading the value from the memory one by one and appending it into the result until we get our null termination string. Alright, now it's time to implement our strlen function. So the simplest way for creating the logic for strlen function is by reading the value from x0 register, because if you remember in ARM calling convention, the first argument of any function will be stored into x0 register, right? So I am going to read the value of x0 register, and since we want it in proper strings, so I am going to wrap it in our function ASCII read, which we have just created. This will give us the proper string, right? Let's print out this strlen and the value which is our ASCII string. Then we know that whenever the function returns, the return value of that function will be stored back into the x0 register. So the register, so by using the register write API, I am going to write the result, which will be the length of this ASCII string. So through length function of Python, I will simply calculate the length of this ASCII string and store the result into x0 register. And then finally I will set our program counter to the value which is in the link register already, because the link register will tell where to return back after finishing this function. So our strlen function is being defined now, and now what we can do is by going back into our callback function, and we will check whether the instruction which is executed is equal to the address of strlen function. So here in Ghidra you see this is the string length function, right? And it's starting from 4c0, so we will compare this value. If it's 4c0, this means that strlen function is going to be executed next, and we have to tell unicorn, instead of executing that actual str length function, execute our custom defined function, right? That's it. So let's go back to the terminal, clear it out, and let's run the script. Boom. So now we have lot of output, and we see that in our strlen function we have our argument test12 which we have passed, right? So in this way we are able to see the arguments which are being passed to the function along with the instructions which are being executed. So now unicorn didn't throw exception here because we have explicitly told Unicorn to execute the function whenever this offset comes up. And then we can see that after this it has executed lot of instructions, but again we end up with this same error. So again we can repeat the same exercise by backtracing it one by one. We see that this is the instruction which is responsible for this exception, and by going to this offset 51C in Ghidra, 51C here, uh, it's pointing to str compare function. Now again, um, this is the culprit here, and we need to define the definition of this function by ourselves, like what we did for str length. So let's come back to the script, and just like this we will define a string compare function. Now if you don't know what string compare function does, again you can go back to the Linux manual page and look for the definition and working of string compare function. Basically it will simply compare the two strings and return either 0 or -1. 0 in case both of the strings matched, otherwise -1. So we will simply first of all initialize the two strings. We will convert the string into ASCII string using our utility function, and then the first argument we know is present in x0 register, so I am going to read that one. So this will be our string 1, and similarly we can get our second string from x1 register, right? And then again for the debuggability purpose, and also you will see why these print statements are useful, because it will show us the real password also. So if I print out string 1 and string 2 here, we will see the password which are being compared. The logic would be simple. We will simply compare string 1 with string 2, and if it's equal, then we will assign the return assign 1 in the assign 0 in the return register, which is x0. Otherwise we will return -1. And then finally we need to tell our program counter to go back where the link register is pointing. Now we need to tell in our callback function if the program counter value is equal to the offset of string compare function, which is 400510, right? So if it's going to be this, then execute our str compare. And if we come back to the terminal and execute the script, hopefully it should be able to run it. And yes, so we have our string length function successfully called, and then our string compare function. And here we see both of the arguments. This is the argument which user has passed, and it's being compared to this argument 1 2 3 4 5 6, right? So this is the real password that we wanted to extract. So in a way our purpose of emulating this binary is solved. We are able to get the real password, but as you see still we are getting this fetch and met because still there are some unresolved external dependencies present in the code which Unicorn is unable to resolve. So if you follow this same approach, you will be able to completely execute the binary without any errors. So that's it about the demo, and I know you guys must be thinking that in real life the binaries are not always that easy, and it's not always possible to re-implement the functions from the external dependencies. So for that, actually I have a trick for you which you can follow. One way is to make external functions work is simply by running the application in mobile in case you are emulating mobile binaries. uh, Otherwise, simply run the binary in your system, and then just before the function execution, try to dump the memory. I mostly work with mobile applications, so I know this. So in mobile memory can be dumped through proc self maps file, and once you have this mapping file, then you can just create and map the segments in Unicorn accordingly. This should resolve all the functions while emulating the code. So I hope you really liked the video and the demo and everything, and if you have any comments for me, then just let me know. Also, if you want me to create video on some other topic, then you can let me know in the comments down below, and I will definitely try to create that for you. Thank you, and see you in the next video.